deposits here, in a mechanism that we don't fully understand, waters are broken down to form molecular oxygen. Cool? So we know previously that oxygen really likes electrons. It's very electronegative. So in this process diagram down here, it must create an oxidant far stronger than oxygen to strip electrons away from this water. Those electrons, think of this as H dot twice. 2 H dots. That dot's not coming off unless you have a good reason for pulling it off. And as we mentioned, this chlorophyll dimer here, this chlorophyll situation, this is P680. They've left off some of the side chain groups just to make it simpler. This thing acts as one, and in this diagram, I took a lot of research, but item 1 here indicates that the first thing when a photon or exciton hits this is an electron is moving over here to pheophytin, which is a chlorophyll without a magnesium. Then, step 2, in a microsecond or less, an electron is being passed to PQ. What does that stand for? Plastoquinone. So PQ is the plant's version of coenzyme Q. Only PQA is bound to this protein complex. It's not moving. And then it passes an electron through an iron to a second plastoquinone. PQB is the one that is hydrophobic and will move in the membrane of the thylakoid. So PQB does the same thing as CoQ in the mitochondria. It's hydrophobic. It can carry 1 or 2 electrons and 1 or 2 protons. Yes? No, it's hydrophobic to begin with. This is a very hydrophobic tail. They're only showing you a portion of the tail. Good question. We don't know, like a lot of why questions in biochemistry. Why does it require 2 plastoquinones? Why not just 1? We have no idea. But this guy really is bound to the protein. He doesn't come off. And then, so in this event, 1, 2, and then an electron, step 3, is being transferred through the side chain of a tyrosine of the protein. This tyrosine was originally called factor Z, and through lots of other additional research, it turned out to be a tyrosine. So they left it as tyrosine subscript Z. Remember we saw tyrosine once before at the second binuclear site in the complex 4. A tyrosine can safely transfer an electron, be a free radical for a moment in time. So here's a tyrosine that transfers an electron back to what would be P680 plus. And as soon as 1 electron leaves, this thing has that redox potential of about 1.3, which says, give me an electron. The tyrosine does that. The tyrosine is going to get that electron from this complex. How? We're not sure which manganese, or is it the oxygen atom? We don't know how this electron is transferred to this. And then, step 5, this thing is moving over to here. So imagine how hard it was to determine the sequence of events. The point is that bumping of an electron to a higher energy state of this dimer right here creates an incredibly hungry compound for an electron. And it's pulling the electron from this water. And this metal complex is the in-between guy. Okay? this is how plants create all this oxygen for you and I to breathe. Here is a look at this oxygen evolving complex. It is a model because, as I said before, it's hard to take X-ray structures that don't disturb the atoms. So this is our best guess as to what this thing looks like. It's got a number of oxygens, 5 of them, that are oxygen atoms. It's got these manganese, and it's got a calcium ion. For a very long time, we thought there was only these manganese atoms, but that turned out to be not the case. So together, they're acting as one, and somehow pulling off this withdrawal of electrons. There are waters that are making bonds to this. Are these the waters that actually, have their electrons stripped away? Probably, but we don't know that for sure. So once again, we see the importance of metals in biochemistry. This metal complex, the calcium, the manganese, somehow are splitting electrons off of waters to make molecular oxygen. It's a very hot topic in research. Here is a diagram that just says basically this is happening, what we just described, one thing at a time. So an exciton comes on, an electron is being passed from the water, presumably a proton is leaving, but we're not sure exactly when, and this happens 4 times, and we're left with molecular oxygen. But most of this is just one giant electron. What we do know is that these protons are being released, and it says them down here, on the lumen side. So these protons are creating, they're part of what creates the giant pH difference across the membrane, which runs the ATP synthase. This is the structure of plastoquinone, which I would only ask that you recognize. And the whole idea is, just like with coenzyme Q, it's doing the same thing. So this plastoquinone has 9 of these isoprene units here. So this 9mer makes this a very hydrophobic molecule. So what this can do is safely grab 2 electrons, 2 protons, as H dots, or it can grab one electron and 1 hydrogen, but it always does it as H dot or 2 H dots. And what this does is it forms the reduced form, PQH2, just like coenzyme Q could form QH2. And so now these electrons and the protons are carried safely on this ring. Now in between, you can have, between these 2 states, you can have a very stable semiquinone, which is when you only have 1 H dot added. So imagine you had just 1 up here, an H dot, and you don't have this other hydrogen down here. This is a very stable, safe way to carry a free radical. Now, the only other thing we have to do is say, well, CoQ, the thing that we've been studying in mitochondria, will make this green. It's got an oxygen in here, so this is an ether linkage, carbon, oxygen, carbon. And it also has an ether linkage there, and a methyl group. The point is, you see that life is using basically the same molecule in the mitochondria. Why, Dr. Hilton, do these organelles want to use this compound? Well, it's very tiny, so it can diffuse very rapidly. very hydrophobic, so it can go in the membrane. And it will pass one electron at a time to where it's needed. And even, I mean, as important as all of that is, it will dump off a proton. And proton gradients are the name of the game to create ATP, unlike glycolysis. So it's a very interesting molecule. So this would be PQA and PQB. They're both the same molecule, just PQA is bound to a protein. And it's passing as part of the circuit the electrons to PQH2. Are we okay with that? Yeah? Everything in green is just the differences. This whole molecule is the same, except for the green part in coenzyme Q. So the mitochondria, again, we think mitochondria evolved from photosynthesizing bacteria. So we're not shocked to see that something with a similar structure has a similar function. But we're always looking at chemistry. Now here is the cytochrome B6F complex. Sorry. If we take a step back, we see virtually the same complex as complex 3 in the mitochondria. Remember, complex 3 is where the Q cycle was occurring. So here, for example, again, these proteins aren't identical to the ones in complex 3, but they're very similar. So here is the one with the hammerhead that we talked about on this flexible arm, and the rest of it's going behind that we can't see. This is the one that is acting as a two-cylinder thing, firing. Here is the cavern inside. That's what I like about this. This is coming from X-ray data, so this is pretty nice. This is not someone making this up. Here is plastocyanin binding. Now, we'd have to go out on a limb and say most likely there is a site for plastocyanin to bind over here. But again, as the thing binds and the thing is shifting, only one site exists to recognize plastocyanin at a time. You follow me? So only one plastocyanin can bind, but there's two landing spots. That's